Okay, welcome to this talk. I'm going to talk about two recent projects of mine inside OpenBSD. One is the Border Gateway Protocol daemon, bgpd, and the other is the Network Time Protocol daemon, OpenNTPD. We're going to start with bgpd. I assume most of you don't know the protocol, so we're going to look at the protocol first for a bit. It's called Border Gateway Protocol. ISPs talk BGP to each other to announce reachability of networks. And networks are subsummarized into autonomous systems. And one ISP is typically one AS, no matter how big he is. Okay, the network reachability is announced with so-called AS paths, which is just the path from the source to the destination described by the AS numbers it crosses. And a BGP speaker usually announces directly connected networks and prefixes with their paths it learned to its neighbors and from its neighbors. Oops, sorry. An AS path just looks like a series of numbers. It's just the AS numbers we cross to the destination, written from left to the right. Okay, BGP knows about 4 messages. Actually, it's 5, but the 5th one doesn't matter. The first one is open, which is sent once when the TCP session gets established. We have a keep alive that are exchanged once the TCP session is there to keep the session alive. We have updates which carry the actual routing information. And we have notifications which are fatal error messages, and well, we hope to never see them. Okay, before we start coding, we look at existing implementations. There's a routing daemon called Zebra, which is under the GPL. It makes heavy use of cooperative threads, and it's not very successful doing so. It suffers from losing sessions when it's really busy. The documentation error messages, if existent, is in Japanese, and the author commercialized it 2 years ago, and well, it's dead. There's another project called Quagga. Some frustrated Zebra users trying to fix the worst bugs. I'm not really sure how successful they are. I don't think they are very successful, but well, anyway. Oops. And we have GateD, which is very old, became unfree, and yeah, it died. Nothing is really left that would be usable. We have Cisco. It's proprietary. It only works on their overpriced routers. It usually works okay, unless you happen to run into one of their Countess bugs. Or the tiny CPUs they love to use in 100,000 euro devices are spammed with work. Juniper's JunoS apparently works okay, but well, it's not free either. So we start designing our own BGP daemon. Of course, we want to have a secure daemon. It's an OpenBSD project after all. This means we have to code really careful. We have to use bounded buffer operations wherever possible. And we should account for our own failure by using privilege separation. From the pains we had with Zebra and Quagga, we don't want to do sessions no matter what happens. This results in the requirement of a fairly independent session engine, which only is liable for keeping the sessions up. And of course, we want to be performant and memory efficient. The full BGP table has 150,000 entries, so memory efficiency is really a point here. Of course, we want a well-designed configuration and filter language. The actual design. We got 3 processes. We got a session engine that only manages the BGP sessions. We got a route decision engine, which holds the actual tables describing the internet in the end. And the routing decisions are taken there. And we have the parent who forks off the 2 other daemons and manages the kernel routing table. We have the 3 processes. Only the master process is running as root. The other 2 processes are change rooted into var empty, which is empty, and runs as unprivileged user. And all those processes are communicating over socket pairs. The parent process maintains the interface to the kernel routing table, and it maintains the interface to the IPsec and TCP/MD5 key management. And the session engine has the listening TCP socket and all the TCP sessions to the neighbors. The session engine, obviously, needs to be non-blocking. And this also means we have to use non-blocking sockets, which means we have to care for all buffering ourselves. Normally, we write something out and write does not return until we are done. Using non-blocking sockets, it can return in the middle, we have to buffer what it couldn't write yet and try later. Of course, that's a lot of work to do by hand, so we invented an easy-to-use buffer API. And for the internal messaging between the processes, we invented another API that we called iMessage API, which actually, the internal messaging is a core component in every privilege-separated program. You have more than one process and they need to communicate with each other, so obviously you need some kind of messaging. The iMessage API and the buffer API worked out so well that I simply reused them for ntpd. In bgpd, we have 44 message types by now, which is quite a lot. And, okay, looking for that session engine. The session engine maintains the listening TCP socket. It opens TCP connections to its neighboring systems. It negotiates parameters with the neighbors via the open message sent for the first, after the TCP session got established. And once the session got established and the open message sent, we have a finite state machine for each neighbor. The updates received from neighbors, the actual routing information, is passed unmodified to the route decision engine. They are not processed in the session engine. And the outgoing updates are generated in the RDE as well, and the session engine just relays them through. So the session engine does no processing whatsoever from actual routing information and only cares for keeping the sessions up. The session engine also maintains a Unix domain socket for the BGP control program, which is used to query runtime information. It's very lightweight. It's typically under 1 megabyte of RAM on an i386 machine. And, well, as said, it runs as unprivileged user bgpd and change rooted to var empty. The route decision engine actually maintains the routing information, which is called routing information base, or RIB, which basically consists of a prefix table, which is the networks, and the AS paths describing the reachability. The BGP filters from there, and the route decision engine calculates the best path for each prefix it knows about. It also generates the update messages as needed. The RIB layout, as said, the full table contains 150,000 entries, so taking care for memory use is a must here. The routing information base is split into many tables. Those tables are heavily linked, so we avoid table walks. Actually, we only need to table walks if you ask the BGP control program to show you the entire routing information base. The update messages, once received, are processed to completion. There's no queuing or something like that happening. And generated updates are queued. We try to use piggyback optimization to get as many updates into one message as possible. And the RB table and sessions can be dumped into MRT files, which is a standard format for later analysis. The route decision engine is very memory efficient in the end. One full view needs around 20 megabytes of RAM. Cisco is about twice as much. For 2 full views, we only need 25 megabytes, so only 5 megabytes more for another 150,000 prefixes. It's really fast. It takes around 10 seconds to load a full view on a 1 gigahertz machine. And it takes less than 5 seconds to dump our own table to our neighbors. If you're used to Cisco, they measure that in minutes rather than seconds. It runs as unprivileged user. BGPD is change rooted to var empty as well, so should we have fucked up there somewhere, an attacker at least doesn't have too much to play with. Parent process. The only process running is root, so we have to take extra care here. It's responsible for getting the routes into the kernel. Only root can alter the kernel routing table, of course, so this has to run as root. It does the next step validation for the RDE. If a neighbor sends us a reachability information for a prefix, we of course have to verify that we actually can reach the IP next stop. Otherwise, we're entering a route to the kernel that is unreachable. It maintains its own copy of the kernel routing table. It does a lot of lookups, and querying the kernel routing table for each lookup to do would be pretty expensive performance-wise, so we decided for our own copy. That means that it has to fetch the kernel routing table and the interface list on startup, and it has to keep it in sync, of course. The parent interface, to keep it in sync, listens on the routing socket. On the routing socket, we see messages about each operation that changes the kernel routing table. The internal view of the kernel routing table is kept in sync by processing those messages we see on the kernel routing socket. If you fiddle with the routing table manually, use route to enter a new route. If you try that with some other BGP daemons, they will crash on you or do the wrong thing. We just noticed that because we get a message saying, hey, somebody else modified our kernel routing table. Well, we respect that, we cope with that, and we won't change a route that we didn't enter to the kernel. The internal list of interfaces and their status is also kept in sync that we use for the next step verification. We do know about the interface link status. And yes, it really means if you pull the cable, we notice that and invalidate the next stop, which is interesting because everybody keeps telling you that's not possible in Unix. We don't need any periodic next stop table walks. A big vendor with a C needs them, walking a table every 10 seconds to recheck reachability. Well, we don't need to. We notice immediately if something changes. The internal view of the kernel routing table can be coupled and decoupled from the kernel. While hacking on bgpd and hacking on SPARC64, which is especially interesting as SPARC64 requires strict alignment and is really pissy about wrong alignment. We had a problem with the KVM space, so I couldn't load the entire table to the kernel, so I added a debug mode to not change the kernel routing table and only work on the internal view. And I realized that it's pretty easy to couple and uncouple them every time. And I sat down and, well, give it an hour, and I had it coded in like 10 minutes, and it was a lot of fun. It's really, really fast. It takes less than 3 seconds on a 750 megahertz machine to couple or decouple the kernel routing table, which is 150,000 messages going over the routing socket and coming back. It needs about 5 megabytes of RAM in the full mesh configuration, which means 150,000 prefixes, which is really, really little. TCP MD5 signatures. BGP sessions are not really authenticated. You just have IP-based access control. It's not as bad as it sounds because it's usually private links, but it's still bad. An attacker could send us a BGP notification. Remember, fatal error message. After receiving a notification, we have to take the session down, which means we lose all routing information associated with that neighbor. If you do that with all my neighbors, I'm offline. So yeah, you don't want that. There's an RFC that defines MD5 signatures for TCP. It's basically an MD5 hash of parts of the header and a shared secret. The shared secret has to be exchanged by some other means with the peer, of course, and the same operation than the hashing from the TCP header and the shared secret is done on the receiving side, and the hashes should match. Unless you happen to run FreeBSD, they don't bother verifying. I don't get the point of implementing TCP MD5 in the first place then if you don't bother to verify the signatures on receipt. This means an attacker has to know the shared secret or break our algorithm. How did we do it? There was very old code for TCP MD5, which dates back to 4.4BSD or even earlier. It never worked. But we still could use it as a starting point, so we did. We implemented TCP MD5 signatures within the IPsec framework as security association. And BGPD got a PF key interface, PF key being the interface for IPsec. Another proof that committee-designed interfaces are really bad. It's like the worst interface I ever had to code for. It's really ugly. And TCP MD5 SIG in the end is extremely easy to configure. You just have to enter a password. It works against Cisco, it works against Juniper, it works against everything else. If you run BGP, please use it. There's no excuse not to. On the other hand, you have to keep in mind that MD5 signatures are rather weak. You have to take care for the key length. Don't use short passwords. And there's an RFC talking about key management considerations when you use the TCP MD5 signature stuff. That's worth a read. So we implemented TCP MD5 as security association in the IPsec framework. So we got the interface already. Of course, we extend that to the real IPsec for us. Basically, BGPD loads the security associations, which, well, is something like the passwords for IPsec, into the kernel. BGPD sets up the flows, which is some kind of routes for IPsec. And then it works. Juniper can do static keyed IPsec as well, and we're compatible, so works, test, use it. Cisco cannot, of course. Well, IPsec on a Cisco, that could cause CPU load, and we all know what CPUs play like. Static keyed IPsec is nice, but actually it would be much nicer if we could have ISA-KMPD doing the keying for us, which means keys are exchanged on a regular basis. We did that, and BGPD just asked the kernel for an unused pair of SPIs, which is some kind of identifier, which usually come from the config file, and we had to exchange the kernel IPsec implementation to give us an unused random pair of SPIs. BGPD sets up the flows. It knows the start and end point already, obviously. It does have a TCP session to its neighbor, or is going to have one. And ISA-KMPD only needs to handle the keying, which means almost no configuration for ISA-KMPD. And everybody who ever configured ISA-KMPD will love that. All you have to do is copy the key files, which are generated for you on the first boot on OpenBSD 3.6 and later, over to the other machine, run ISA-KMPD -KA, and you're done. That's it, really. Integrating BGPD to our packet filter, PF. The BGP protocol is used to exchange routing information, but it's also a very efficient way to exchange lists of networks or IP addresses. And thus it's very interesting to integrate BGPD with our packet filter. So we did. BGPD can add prefixes, networks, IP addresses it learned from neighbors into a PF table. The prefixes are selected using the filter language, and, well, tables internally use a radix tree. It's really fast, even with a lot of entries. And, well, PF tables can be used for pretty much anything. You can do packet filtering, you can do redirections to spamd. BGP distributed spam blacklists are pretty interesting. You can do quality of service processing, just slow all those weary senders down. CARP, the Common Address Redundancy Protocol. It's a protocol where two hosts can share an IP address in a master-slave scenario. When the master fails, slave takes over. It's kind of VROP, but without the pattern problems, and it's better, it's faster, and it's address family independent. Typical case, exchange points. You get exactly one IP in the exchange point network. What about using two machines instead of one, and use CARP to fail this one IP address over between those? It works without special support from BGPD, but we actually can do better. If we make BGPD aware of the CARP master backup state, which actually is the link state for the interface, so it's easy to figure out, then BGPD can can keep the sessions that depend on a carp interface in idle state as long as the interface is not master. And the very same moment the interface becomes master, it can immediately start connecting to its neighbors. So you have a much faster failover time. We are going to take a short look at the configuration, a really short one. It's split into 5 sections. Macro definitions, just like in PF, basically variable assignments. Global settings affecting the operation of bgpd as a whole. Networks we want to announce, our neighbor definitions, and of course, filters. Macros are pretty easy. You pick a name and assign some value. You can use them later by prefixing a $sign. Global configuration, all you really have to give is your own AS number. Everything else, there's sensible defaults. The FIB update is whether the kernel routing table is coupled or not. And of course, the networks you want to announce. A neighbor definition. Well, you define a neighbor. All you have to give again is the remote AS number. Everything else can be figured out or has sensible defaults. We're using TCP MD5 passwords here. You see it's just one line in the configuration file. It's really easy, but please use a different password. Really cool is the announce keyword. You can set it to none, which means we're not going to announce any networks to that peer. Or you can set it to self, which means we are going to announce all networks from our own AS. Or you can set it to all, announcing everything we know, or a default route. Then we're going to announce a default route and nothing else. This is very cool because on Cisco and Zebra, you need to write filters for that. Complicated filters, and here it's just one keyword. You can group neighbors, and the neighbors just inherit the settings from the group. We have an example for IPsec with static keys, which still is pretty easy, but long keys. And much nicer is using bgpd with ISA-KMPD to do the keying for it using IKE. Then it's really easy. All you have to do is IPsec, ESP, IKE, or HA IKE. All you have to do is tell bgpd, hey, we're going to use IPsec on that connection. Filter language, we're only going to take a brief look. It looks like PF on purpose. Looking at the BGP control program, which is the client to query runtime information, it connects to BGPD using a Unix domain socket. It can query runtime information. It can cause a configuration reload. It can couple and decouple the kernel routing table anytime. It can take specific sessions up and down. And I'm too fast again, sorry. Here's an example for the summary view, which BGP operators usually look at pretty often. Just listing all the sessions we have. Actually, I had to cut this a bit to make it fit, but I hope the relevant stuff is still in here. Basically, you see the description of the neighbor, his AS number, the number of messages sent and received, currently queued messages for him, which of course is always 0. And last time the connection either got up or down, and with the prefixes we learned from our neighbor, including a limit if we set one. Okay, status quo. It's very stable. It's in use at quite some sites. Actually, I'm surprised how fast it got adopted. This includes sites with many peers. There's a guy in Australia running several hundred peers. I have no idea what he's doing, and he's not going to tell me, but, well, whatever. If you set up BGPD, please send me email. I love getting that mail. Some statistics for BGPD. BGPD itself is close to 18,000 lines of code, with like 1,400 lines of code for BGP control, and yeah, we have man pages. It's another 2,500 lines. Future plans, and especially evil future plans. Give PF access to some more information from BGP. Allow for free text labels attached to a route. That's 32 extra bytes we can attach to any route we enter to the kernel. That's already implemented in route, in the route utility and the kernel routing table, and PF can actually already filter based on it. BGPD cannot set that yet, but I'm going to code that soon. I'm saying that since a year, but I'm really going to do it soon now. This allows for really evil shit. You can pass in everything that matches a route from German Telecom and put it into a really slow queue. And finally, you can tell your customers, I always told you they're slow. Switching over to OpenNTPD. NTPD, the network time protocol. There's one implementation that everybody uses. Of course, we've not been very happy with that, so we started designing our own one. Again, primary design goal is security. There have been problems with the other implementation. We don't want to repeat their faults, of course. So what we need to do, very tight validity checks in the network input path. All buffer operations, again, have to be bounded. And again, we have to account for our own failure by using privilege separation. Second goal, ease of use. The other implementation is really hard to configure, and we want a lean implementation which is sufficient for a majority, which means we don't want an overloaded feature monster supporting every possible NTP use in the world. If it fits for a majority, it's fine. If you belong to the other 1%, please go around the other one. It should just work in the background without much fiddling and monitoring and management. And it should reach reasonable accuracy. Reasonable means we want to get close, we want to have something that's good enough for our log files, but we really don't care for microseconds that our system clock cannot express anyway. And yeah, it should require a minimum of configuration to be easy, of course. It should be fast, needless to say. Looking at the protocol again, really fast because it's that simple. There's a much chatty IRC about it. The protocol, really that simple. The math to do is a bit harder, but it turned out the IRC is actually describing an implementation and not a protocol. And well, it accounts for an accuracy that's completely pointless on a Unix box because it's far above the tick frequency of the kernel system clock. Yeah, so the IRC is really bad. I'm not surprised. The IRC needs far more than 100 pages to describe the network time protocol, and well, I'm going to show you the only wire format. It's so that simple. They have 64-bit timestamps, 32-bit integer part, and 32-bit fraction. We have 32-bit timestamps for informational stuff, half the resolution. And this is the entire NTP packet as it appears on the wire. I don't need 100 pages to describe that. The timestamps. There are 4 ones that are really important. One is the so-called original timestamp, which is the time the request got sent by the client. We have the receive timestamp, which is the time the query was received by the server. The transmit timestamp, time the server replied. And destination timestamp, when we finally received the answer. Given these 4 timestamps, the local clock offset is now pretty easy to calculate. Formula is here. Questions? Again, we use privilege separation, so we are going to have 2 processes, a parent which runs as root, and which main task is to fork off the real NTP engine, which then runs as usual NTP, and change routes to var empty again. In between we have a socket pair, of course, and because I'm a cheap bastard, I'm of course reusing the buffer and iMessage framework that I already wrote for BGPD. And we got 3 message types. Remember, BGPD had 44. We have 3 here. It's iMessage adjust time, iMessage set time, and iMessage host DNS, which we're going to look closer at in a few. NTPD is actually a really good example if you want to learn about privilege separation. It is simple enough to be easily followed and read and grokked. And the message types show the 2 common reasons we have to privilege separate for, instead of just dropping privileges. iMessage adjust time. The NTP engine asks the parent to do the adjust time call, syscall. Why do we need to first separate that? Adjust time requires root. Second message type, well, iMessage adjust time, set time is just the same as adjust time. It just sets the time hard instead of adjusting slowly. The second class of messages, we have iMessage host DNS. The NTP engine asks the parent to resolve host names. That does not require root, but it requires access to etcresolve.conf, IP maps and whatnot. And remember, we are change rooted, so we have to ask the parent who's living outside the change root to do that for us. Very important. You have to do very, very, very strict validity checks when you receive messages from the unprivileged child. Always assume, well, it's untrusted. Always assume it's already compromised. If something's wrong with the message you receive from the unprivileged process, fail immediately and hard, exit, kill it. Don't try to recover, you can't, and likely your child is compromised. Just assume it's compromised, exit, fail, log, and don't ever talk to the client again. This was the last SSH fuck-up, talking to the client again afterwards. Implementation, server side, should be really easy. Just call receive from, get the packet, decode the request, get time of day to get the current time, build the reply, and call send message to send it out. Unfortunately, it's not that easy, because doing so, we might reply with the wrong source IP address. Our reply might have the wrong IP address as source if the machine has multiple IP addresses. We are talking about a UDP protocol, it's stateless, so we have no idea on which of our IP addresses we actually received the packet on. Many implementations will refuse our answer if the source IP address is wrong. And our solution is to listen on each individual IP address so we know on which IP the request was sent to by just knowing on which socket we received the packet. This is unfortunately the only portable hack to write UDP servers that have to take care for the source IP addresses. We're using GetIF address for that, except for on Solaris where it's not available. So unfortunately on Solaris you have to specify the listening address by hand, at least until someone gets a clue and implements that. The client side is a bit harder. We have to send the queries to all of our peers. We have a little state engine so that we don't wait forever for a reply to be received. On receival of the replies, we calculate the offsets and all that stuff. And when we collapse the offsets, we learn from our neighbors into a single offset and call adjust time to ask the kernel to slowly adjust the clock for the account for the offset. Unfortunately, that's a little bit more complicated too. To increase accuracy, we need to filter the replies we get. There's a so-called clock filter implementing an algorithm by David Mills, who's the author of the other NTP implementation. It basically works like you get eight replies back from each peer and figure out which of those 8 had the lowest latency on the network. And you're picking that and invalidate all older replies. Bad network connection results in poor accuracy. This means we have to punish peers with a bad network connection. The only way to figure that out currently is packet loss. Once punished, a peer needs to send us a few good replies before we trust him again. In the query we send out, the transmit timestamp. We need the transmit timestamp when we receive the reply from the server to know when we send the reply out, but actually we can remember that locally. So we can use the transmit timestamp field for something else, and we do. We put a 64-bit cookie into that field. All servers are required to copy that timestamp verbatim into the original timestamp field in the reply. They are not allowed to change it whatsoever. So upon receival of the reply, we check that the original timestamp matches the cookie we send out. This is a really cool hack, extending NTP security. It's really cool because it doesn't have any drawbacks. Fault stickers. What if some server deliberately sends us the wrong time? There's an incredibly complicated implementation of a fault stickers detection in the ntp.org implementation. Of course, that can only work if you're querying a reasonable big set of servers. If you're only querying one server, you have no way to tell whether the time he sends you is right or not. So you should at least query 3. And well, we can filter away false stickers much simpler. Unfortunately, we cannot detect them easily. After the clock filter ran, we have one reply per server, one collapsed offset. To get the local clock offset, we take the median offset from all replies, not the average. Let's look at median shortly. Basically, you order all the offsets you got from your peers by value and take the middle one. In this example, the middle one is 14. Well, 14 is pretty good. Look at the average. The average would be something like 350. If you look at those values, you know which one's wrong. Coping with big offsets at startup. If the local clock is several hours or 30 minutes or even more off when you start ntpd, it has to account for the offset somehow. Adjust time would take literally days or weeks to account for that. On boot, it's pretty okay to run something that sets the clock hard to the correct time. Usually ntpdate or in OpenBSD rdate, which speaks ntp2, is used for that. But OpenNTPD can do that itself now. You don't need a second thing to configure, and there's a command line option -s, which unconditionally is unconditionally added by our RC scripts, which sets the time hard on startup and then never again. We are never going to change the system clock again. We are only going to adjust tick frequency using adjust time. So, getting started with OpenNTPD, how-to style. How to sync your OpenBSD 3.6 box clock to a set of random public time servers. You echo NTPD flags or set NTPD flags to nothing in rc.conf.local and reboot or start NTPD. And I'm not kidding you, that's it. There's no further configuration needed. Looking at the config file, this is actually the default configuration we ship. There's just 3 statements, listen, server, and servers, and per default we have servers pool.ntp.org, which is a pool of public time servers. The listen statement, tell NTP where to listen. Listen on star, listens on all IP addresses using a diff address, doesn't work on Solaris as said. You can listen on a single IP address and you can have that as many times in your config file as you want, and we're going to listen on all those addresses. Server, sync your local clock to a single server. If that's given as host name and it resolves to more than one IP address, we are going to query the first one, and if we don't get a reply back, try the second, and so on and so on and so on. The difference to the servers keyword, if that host name resolves to more IPs, it's expanded like you had given multiple server statements, which is really neat for pool.ntp.org and similar DNS-based pools. Okay, status quo, where are we? It's just 3,000 lines of code with only a really tiny fraction running as root. The accuracy is typically around 50 milliseconds. That's good enough for most users. That's the system clock's accuracy. Your Unix kernel has a tick frequency of 100 Hertz. This is 5 ticks. Expecting any better from a standard Unix kernel is stupid. The performance is really good. Actually, the time server I run on our network for about 100 machines is the slowest VAX I could find, and I still cannot measure the CPU load and TPD causes on that machine. Of course, everybody loves how easy to use it is. You just start it and it works. Future ideas. We need some permanent tick frequency adjustment. If you figured out that your system clock goes wrong by 1 picosecond every hour, it would be nice to permanently adjust for that. That needs kernel support, that's coming, but well, it's not done yet. We could use better filtering, especially detect outliers and punish peers. Maybe support GPS clocks or DCF77 clocks, or how it's called. And that's it basically for OpenNTPD. I have to thank a few people. Claudio and Andrew, who are working with me on BGPD. Alexander Guy, who worked with me on NTPD in the early days. He left the team, unfortunately, now. And Theo for kicking my butt, design help, and much too much beer. I also have to thank Wim for continued support and especially beer supply. Thank you, Wim. Please do him a favor, don't ask him about the minibar in the hotel. And over the last page, in short, we want your money and we want beer. Thank you. Questions? Yeah.
Are you aware of any commercial products that make use of the two of your programs, especially the BGP code?
I'm not. Darf ich auch noch? Ja. I'm not aware of any yet.
But I could imagine that especially the BGP code might be very interesting for vendors of firewalls, for instance.
Yeah. Yeah, I expect that too, but well, it's still pretty young. It's just, what is it now, 16 months or something? Actually, it's just 13 months, so give it a little slack, it will happen sooner or later.
Another question, could you maybe...
Oh, it's still you?
Yeah, sorry. Could you give us an idea what operating systems these applications run on, because they seem to be tightly coupled with the kernel?
BGPD is very coupled to the kernel. That's not my decision, that's just how it is. I mean, you have to manage 150,000 prefixes. That takes quite a little bit of KVM space in the kernel routing table. The BGP daemon is ported to FreeBSD, where it lacks IPsec integration and TCP MD5 and something else. So it doesn't support all features on other platforms. It's not ported to any non-BSD because the interface to the kernel routing table, of course, it's not standardized. On the other hand, the interface to the IPsec stuff that I talked about is standardized. It's so well standardized that it doesn't even work on FreeBSD. Great standards. The ntpd daemon runs on, I'm not doing the portable. The portable is done by the same people that do the OpenSSH portable. It runs on all the BSDs, on Solaris, on HPUX, Mac OS X. I don't know what not. It's probably a question of trying it. It should be pretty portable. The portable changes are like 5 lines of code. And 500 lines of configure script or something. More questions?
Is all of this stuff on the 3.6 distribution?
Oh, I should repeat the question. The question is whether all of that is on the 3.6 CDs. Both OpenNTPD and OpenBGPD are on 3.6, yes. More question, don't be shy. Well, no questions left. I did my job, obviously. Thank you.